Hello, my name is João Miranda Lemos, and this is the first part of a course on control of nonlinear systems. This course is supported by chapters 6 through 9 of the book Controle no Espaço de Estados that you can follow if you are able to speak Portuguese. If you are not able to speak or read Portuguese, the Portuguese language, you can still listen to this lecture and follow the slides that are mostly written in English. The summary of the whole course consists of 4 parts. In the first part, that corresponds to this lecture, we introduce the state model of nonlinear systems. Then we will speak about linearization, and here we will study the stability properties of equilibrium points of nonlinear systems, as well as how to design controllers for the linearized models. Then in the third part, we will be concerned with Lyapunov's direct method, which is a more powerful method than linearization. And finally, in the fourth part, we will capitalize our knowledge about Lyapunov's direct method to design nonlinear and adaptive control laws. So in this lecture that you can see in this video, we will start by studying the state model of nonlinear systems. And the idea is to show how a state model can be written, how the state model equations can be written for a number of nonlinear systems, and to show that this state model is written in a common pattern to different examples, and also to give a number of examples in which that show that the behavior of nonlinear systems can be quite different from linear systems. And the part of the book that is related to this lecture, the part of the book Controle no Espaço de Estados, is chapter 6, as you can see in the slide. Now, if you look at the book, chapter 6 has a funny name. The title of chapter 6 is The Biology of Non-Elephants, which is a somewhat improbable title. And why is this so? Imagine that you are a biologist and you want to study elephants. So elephants are characterized by a number of features. They have big bodies. Since they have big bodies, for instance, they must have big ears to dissipate the heat generated by their metabolism, and so on. You can find of some unifying properties for elephants that shape their physiology and biology in general. Now, suppose that after studying the elephants, you want to study non-elephants. While elephants is a class of animals that are quite well defined and have strong unifying features, non-elephants can be anything from Paramecia, which is a unicellular being, to the giraffe, or to the bat, or whatever animal or being that you want to study. And this is an example to show the difficulties that you have when you pass from linear systems to non-linear systems. So linear systems have an important unifying property, which is they verify the principle of superposition. And from the fact that they verify the principle of superposition, you can derive a number of properties verified by linear systems. Now, in nonlinear systems, you don't have such unifying property. So it is not surprising that you will find wildly different behaviors, and I will show you some examples. To start the course, I will provide some examples of nonlinear systems. These examples were selected because they illustrate a number of interesting features, but we could also give many other examples. So the examples that we are going to see are solar collector thermal plants, chemical reactors, robot arms, and phase modulation communication systems. Now, let's start with the first example, parabolic through solar thermal collector fields. How is this made? Well, the objective is to collect solar energy and to transform it in the form of thermal energy. And you can see here a sketch of one example of a solar thermal field, actually the parabolic through solar thermal field. How does it is built? It is built by, it consists of a mirror that you see here. It's a parabolic mirror that points at the sun and concentrates solar rays along a pipe that flows at their focus and at its focus. And inside this pipe, there is a liquid that accumulates thermal energy, and you can manipulate the flow of the liquid by using a pump, and you manipulate the manipulated variable is the command of the pump. Actually, this is by itself a control system, but let's assume that you have a signal that allows you to impose the flow. So if you measure the flow of the pipe at the outlet of the solar field, as in here, you have a temperature measurement. And if you want a higher measurement, you will reduce the flow. If you want a lower temperature, you will increase the flow. That's very simple to understand. And you can see here one example of a solar collector field in the south of Spain. Now, how can we model this? We have temperatures along the pipe. So each point of the pipe has its own temperature. So you have a variable. You can define the temperature by a variable capital T, which is that represents the temperature at position Z measured along the pipe, and that time T. So the first difficulty is that you have an infinite number of points in the pipe. So you have an infinite number of points where you measure the temperature, and you need to describe the evolution of the temperature by a partial differential equation, which is written here. And you see, this is not so too complicated. It says this differential equation says that the partial derivative of the temperature with respect to time is equal to minus the flow times the partial derivative of the temperature with respect to the position Z along the pipe, plus a term which is proportional. Alpha is a proportionality constant proportional to the solar radiation R. And here U is the flow. How can you obtain and prove that this equation holds true? Well, we are not going to do it, but if you do an energy balance, then you can derive this temperature. And basically, it says that the change of temperature in time is due to two effects. One effect is the second one, which is the temperature rises due to solar radiation. So alpha is a positive constant. And the other term says that you are moving to the right in the sense of the flow. Okay, this is not completely obvious, but the proof is very simple, although we are not going to do it. Now we have one problem, and the problem is that this is an infinite dimensional system, and we don't know how to deal with infinite dimensional systems. Why infinite dimensional system? Because the state is a function of time, is a function of space and time. So at each time you have the space which is has an infinite number of values. So the temperature at all possible points in the segment of the pipe. Now, how can we proceed? We can do an approximation by a finite dimensional state model. And what do? You consider the pipe divided in points where you measure the temperature, or you think that you measure the temperature. And now, to relate the temperatures at these points, so you have points at delta, 2 delta, 3 delta, and so on, I delta, you have temperatures that I call x1. X1 is the temperature at time delta, so x1 of t is the temperature at position delta at time t, x2 is the temperature at position 2 delta at time t, and so on. And now, to relate these state variables that are now in a finite number, then we are going to approximate this space derivative, so the derivative with respect to the space dimension, the partial derivative with respect to the space dimension. And of course, at each temperature, you are fixing the position, so this partial derivative becomes the total derivative at that position. And the partial derivative with respect to z becomes the increment of the difference between the consecutive temperatures divided by the increment in space delta. So you can write this equation relating two consecutive points, and if you write it for all the points for I equal to 1 up to n, you get a state model. And you can say now what I measure is the temperature at the outlet of the pipe. So your y is going to be xn of t, so temperature here. So your state model is formed of these n ordinary differential equations for the temperatures in the positions of these specified positions of the pipe, plus one output equation, which is this one is just yt equals to xn of t. And you can see that you have products between the manipulated variable u, which is the flow or proportional to the flow, and the temperatures. So these are nonlinear equations. So in general, you can say that this is function f1, this is function f2, and so on. So you collect all these functions in a vector f, and you get x dot equal to f of x u, and y equal to h of x of t. And h in this case is just the component, the last component, xn. So this is a standard way of writing the state model. In the linear case, f is equal to ax plus bu, but in this case, f is given by the functions that you can see here that are equal, that give you the derivatives. Let's see another example. Another example is a chemical reactor. It's a continuous stir tank reactor. What is a continuous tank, the stir tank reactor? Well, it is a tank. Think of this as a tank. This tank can be very, very small, say 1 liter, but it can be very large. There are reactors of this kind that they have about more than 10 meters high. So imagine a building of 3 stages. That is the size of this tank. And it is steered, so you have a motor and you have some elements that rotate, and they force the liquid inside the tank to uh, to be mixed. So the importance of being steered is that we are assuming that the liquid inside the tank reactor is homogeneous. So you can characterize it by just a finite number of state variables, say the composition of the liquid. If it is just one chemical species, then you can just have one state variable. Now, why continuous? It happens that you are always pumping or allowing some reactants to enter the reactor, and you are always extracting by the output the products of the reaction. In this case, we are assuming that we have inside the reactor a reaction in which the chemical species A is transformed in chemical species B plus heat. And this heat has to be liberated. So you have a jacket which is a kind of hollow cylinder around the reactor, in which you inject refrigeration water. The water removes the heat, so there is an output of refrigeration water. And we assume that we control the temperature here, or leave it. In this case, we are going to leave the temperature here without any control, just a steady flow of water. How can we? So continuous means that you are continuously adding products that react and that they produce some products of reaction. How can we model this equation in particular? Well, you can do a mass balance or a species and an energy balance, these two balances, and you end up with these two equations. The first is concerned with the mass balance. The second is concerned with an energy balance. And Ca is the concentration of species A, and CAI is the manipulated variable. So it's the concentration of species A at the inlet reactants. You might wonder, what happened to Cb? Well, by conservation of mass, Cb can be computed in an algebraic way from Ca, so we don't include it in the state. Now, the temperature is important because you see that the rate of decay of the Ca, which is associated to this term here, depends on the temperature by an exponential term. This is the so-called Arrhenius law that you study in chemistry. Well, if you never studied chemistry or you never heard about the Arrhenius law, it's no problem. Just notice that E and R are constants, and we have also K0, and we have an exponential law dependence on temperature. And then you have also this other equation. Now, we can think, for instance, of, well, first of all, we have this form of the equations. This is F1, this is F2. So F is the vector field, is as these formulas here. Remember that U is CIA and X is made of the Ca and T. And Y, well, you can define what is Y. You can say that Y is, for instance, the concentration of A in the output of the reactor. Now, you can wonder one thing. Is that are there values for the state for which the concentration and the temperature remain constant? These are equilibrium points. Let's think about the temperature. You are generating heat due to the reaction, but you are also removing heat with the jacket where the cold water flows. So when you are generating as much heat as you are removing, you will have an equilibrium. And in this plot here, you can see in the horizontal axis the temperature of the reactor. And then you have two curves that represent, well, the straight line is the heat removed by the cold water that flows in the jacket. It's proportional. This heat, removed heat, is proportional to the temperature. And then you have this shape, this S-shaped line. We call it a sigmoidal line because of having a S shape. It's just a name. That represents the heat generated by the reaction, and this has an S shape because of that funny dependency on the exponential of the temperature on an exponential function, the so-called Arrhenius law that I mentioned before. So you have 3 points A, B, and C where these two curves met. And when they met, it means that you are removing as much heat as you are generating. Now, so take, for instance, the situation B for temperature T2. And suppose that for some reason the temperature increases for T2 prime. At temperature T2 prime, what happens? You are generating this heat due to the reaction, but you are only removing a smaller amount of heat with the water cooling. So there is accumulation of heat, and the temperature will tend to increase and go away from the equilibrium point. If you think that you are at a lower temperature, then it's very easy to see that now you are removing more temperature than the one that is being generated, and again your temperature will be decreasing. So T2 is an equilibrium point, but it's an unstable equilibrium point. And you can do a similar reasoning for points A and C and conclude that A and C are stable equilibrium points, so that if you are if the temperature increases by some value, then you will return to the temperature, provided that the change is not so big. So we have an interesting thing here, which is, first, we have three isolated equilibrium points. This is something that is impossible to happen in linear systems. Later we will see it with care, but in linear systems, either you have the origin as the only isolated equilibrium point, or you might have a continuous of equilibrium points, not isolated, not several isolated equilibrium points. And the other thing which is nice is that one of the equilibrium points is unstable and the other two are stable. So it's pointless to say that the system is stable or unstable. What you can say about stability is concerned with equilibrium points, not with the system. So in a linear system, you can say, well, the system is stable or unstable because you are mentioning only one possible equilibrium point, isolated equilibrium point. But in nonlinear systems, you should never say it's a stable system or unstable system. You can only use these qualificatives to points, to equilibrium points. Now, another example, a robot arm. A robot arm is simple, very simple robot arms. You have some motors at these joints. You have two joints. You have these angles that are generalized coordinates, and you can write these equations in this form, okay, using This is a classical example in robotics, so I'm not going to go into detail, but you can use Lagrangian mechanics, for instance, to write an equation of this, where h is a function of q, and c is also a function of q and the derivatives q dot. And t is the vector of torques applied to the joints. Now, we can define state variables to be both generalized positions, both generalized coordinates, and then their derivatives, and define u as the applied torques. So you can write these equations in this form. So again, you have something which is of the form x dot equal to f of xu, where f1 is x3, f2 is x4, and then f3 and 4 are melted here, lumped here in this equation. Now, one example from a phase modulation communication system. So in a communication system, you have an emitter, you have a message, then you have a modulator, and you have a channel, and you have a receptor. Okay, and the receptor receives some signal from the channel and is able to reconstruct an estimate of the message that I called m hat. So imagine, for instance, that you have some dynamics for generating the message that it is the product of a linearized system, of a linear system, and you have a phase modulator. So the signal that you are sending through your channel is the cosine of some frequency, but in which you have a phase that is proportional to the message. Okay? So what you observe is this cosine, perhaps with some noise, and then the problem would be to estimate m through observations of y. But in this case, if you just think about describing the modulation, the representation of the system, you could say, well, I have again my old x naught equal to f of x, and y equals to h of x, in which h is now this cosine function. Okay, so what is the big message up to now? The big message is that you can describe many widely different systems in this form. So you have a dynamic equation, x dot equal to f of x and u, with some initial conditions given. Then you have an output equation, which in general can be a nonlinear function of x and u. And in discrete time, you can also have a similar equation. Now, x of k plus 1, where k is the discrete time, is f of the previous state in the previous input, and y is an instantaneous function, a static function of x of k and u of k. How can we simulate this system? Very simple. Very simple. So you will need just two blocks. One block is a battery of integrators, and the other block is a nonlinear function. So if you have a block of integrators, suppose that you force somehow the derivative of the state to be at the input of this block. Then if you integrate the derivative of x, you get x at the output. So to force the derivative, your nonlinear system, your nonlinear function must be a function that maps u and x at input to dx dt. So you connect the output of this block which is your f function, to force it to be the xdt. And you impose the initial conditions by imposing the values of the integrator. So in this way, using just a nonlinear function and a block of integrators, you can easily simulate nonlinear systems, or at least nonlinear systems that can be written in this form. They are not all, but they are most of the ones that you are going to consider in your lifetime. Now, we should be careful. Remember the story of the elephants and the non-elephants. We are dealing with non-elephants. So when we move from linear systems to nonlinear systems, we can have different phenomena appearing, different features. We can have the possibility of non-unique solution, multiple isolated equilibrium points. We have seen already one example with the chemical reactor, critical dependency on parameters, and singularities in the time response. Let's briefly discuss these points by providing some examples. So, first of all, unicity of solution. We would expect that if you have your state equation, let's think now that you don't have your input function. Okay, so it's an autonomous system. Once you specify the initial condition, the solution of X is unique. Actually, this is not always so. So I'm going to show you one example that contradicts this intuition. But you can impose conditions on the function f, on the vector field function f, to force that the solution, once the initial condition is provided, is unique. And these conditions are, for instance, that the partial derivative of f with respect to x, that is to say, the Jacobian matrix of f, is continuous in the neighborhood of x0. So for a set of states around the initial condition, the Jacobian matrix of f is continuous. In linear systems, the solution always exists. Why? Well, that's because f is nothing more than ax, and the Jacobian is nothing more than a matrix of constants, and the constant is continuous. So linear systems are always well behaved in the sense that they have a continuous solution once you specify the initial condition. But in general cases, this is not so. Let's see one example. So consider this equation in which x is scalar and the dt is the cubic root of x. Well, looks quite pacific, peaceful, and you have some initial condition which is x of 0 is 0. Now, one solution that verifies this equation with this initial condition is just to ask that x of t is 0 for all possible t's. If you replace it here, is immediate. Another solution is this one that is written here, 2/3 of t up to 3 divided by 2. So the square root of the cube of 2/3 of t. You can verify that this verifies, it's immediate to see that if it verifies the initial condition, because if t equal to 0, this gives you 0. So it verifies the initial condition. To verify that, to check that it verifies the initial, the differential equation, it's also very simple. It's just a matter of differentiating this expression with respect to time, plug it here, and see that we have a true identity. So we have two solutions that are not the same, but they share a common initial condition. Okay? What happens is that if you compute the Jacobian of f with respect to x, which is in this case just a scalar, you get this expression. And for x equal to 0, because this is the inverse of x up to 2/3, it will be 1 divided by 0 would be infinity. So this is not continuous for x equal to 0. And so we cannot, of course, invoke the unicity theorem that we just have presented. So there are these examples, and we must be careful. In many cases, systems that have a non-unique solution are a kind of mathematical monsters without any engineering interest. So we rule them out. So we are going to say, well, we assume tacitly that we are going to consider only examples in which the Jacobian of f with respect to x is continuous at all states. But this is not always so. Actually, there is one important situation, which is magnetic suspensions. Magnetic suspensions, you have non-unicity of solutions that might yield some funny phenomena, in particular with respect to frequency response. But this is something that it's out of the scope of this course. But bear in mind that in some cases, we have to be confronted with these situations. Anyway, hereafter, I'm going to assume that the f dx is continuous in the neighborhood of the initial condition, so the solution exists and is unique. Now, let's say something about equilibrium points. Equilibrium points of dx dt equal to f of x are values of the state for which, if you start at these states, then you remain there. So if they are constant, it means that dx dt is equal to 0. So you can easily obtain, at least from a conceptual point of view, you can easily obtain the equilibrium points by solving this nonlinear algebraic equation, f of x equal to 0. Of course, in general, you must resort to numerical methods, and there is an abundant software for that. This is an example that I'm going to skip. Now, suppose that your system is linear. Then the equilibria are given by the solutions of ax equal to 0. Now, you have to distinguish between two situations, A being invertible or A not invertible. If A is invertible, then you can solve this equation as x equal to the inverse of A times 0, and this means that x equal to 0 is an equilibrium. So if A is non-singular, there is a unique equilibrium point, x equal to 0. But if A is singular, then not all of its lines are independent, and you can find some values of x that are orthogonal to all of these lines, and these values of x define a subspace of the state space in which ax is equal to 0. So this subspace, this hyperplane, if you want, is a set of equilibrium points. So in linear systems, either you have just an isolated equilibrium point, which is x equal to 0 when A is invertible, or if A is not invertible, then you have a continuum of equilibrium points. Now, let's see another example of multiple equilibrium nonlinear systems. Later, we will see more along the course. Suppose that x is a scalar, and you have this equation. Now, the equilibrium points are given by equating minus x plus x squared equal to 0, or solving this equation. And you can easily see that x equal to 0 and x equal to 1 are equilibrium points. So remember, if the system was linear, you could only have an isolated equilibrium point. If the system is nonlinear, you can find examples in which you have multiple isolated equilibrium points. Now, let's examine another issue, which is singularities of the solution. Consider this equation. Consider this equation. dx dt equals to x squared, and with some initial condition, x of 0 equal to x0. You can solve this equation using separation of variables. Well, if you don't remember what is the method of separation of variables, it's not important. Believe in me, trust in me, that the solution is given by this formula. So for t equal to 1 divided by the initial condition, at this time, t equal to 1 divided by x0, this becomes infinity. Okay? So you have a solution which starts at x0, and for t, in this case, x0 was 0.2, the inverse is 5, so at 5 you are at infinity. So in less than 5 units of time, you reach the infinity. This is something that can never happen in linear systems, because in linear systems, you go to infinity according to exponentials, or exponentials multiplied by time polynomials of t. They reach infinity, but they take an infinite time to reach infinity. And you can see that in this example, you could reach infinity in a finite time. Now, two important aspects are, for which systems does this happen? And the second issue that we should say something is, what are the implications of this fact? Well, for the first, the situation is very simple. If f is supralinear, that is to say, if f grows faster than a linear function, then it has a faster growth with respect to components of x than a linear function, then you have this phenomenon. This means that when you are building models, you should be careful with the powers. Now, as for the second one, what is this useful for? Well, it's an interesting mathematical fact, but it has a direct impact on control of nonlinear systems. Remember what we did in control of linear systems with state feedback, and when you are not able to feedback the state, use an estimate produced by a state observer, an asymptotic observer. And then we had the separation theorem, and the separation theorem is something that tells you that you can impose the poles for the state feedback, the so-called controller poles, and the poles for the estimation error. And you can design both things separately and then put everything together. The fact that you have such phenomena in nonlinear systems prevents you from having a separation theorem, because in the state observer, if you are able to design a state observer, imagine that you say, well, I'm going to have, for instance, a state observer which is a replica of the system, and then I re-inject the output. But it's a naive state observer. Sometimes it works, sometimes it does not work. And even when it works, it can happen that due to the nonlinearities, you have such a phenomenon. And if you have such a phenomena, the error, the estimation error, goes to infinity much faster than the controller is able to regulate the system. So this is one reason why this type of phenomena is a limitation in nonlinear systems, and we should be careful with it. It's not just a mathematical curiosity. Although we will not explore this further. Now, one thing that attracts a lot of curiosity is critical dependency on parameters. Consider this example in which you have two state variables, and mu is a parameter. So you have x1 and x2 state variables, and mu is a parameter. Now, if mu is smaller than 0 and bigger or equal than -1, all the solutions converge to 0 when t goes to infinity. But if mu star assumes the value 0 or positive, then there is only one periodic solution and the origin becomes a node. So we have these two situations. For mu equal to -0.1, for instance, the states converge to 0. So this is the evolution of states in time. This is the evolution state trajectory. So this is x1 in the vertical x2, and you are spiraling towards the origin. So the origin is an asymptotically stable point, and you have no periodic solutions, nothing of the kind. Now, suppose that you change mu a little bit, you increase it, and it's now positive, but you just increase it by 0.2. And then what you see, a periodic solution appears. A periodic solution appears here, okay? So this critical dependency of parameters in which the structure of the response changes wildly when you increase some parameter or when you vary some parameter is typical of nonlinear systems. In this case, this is called a bifurcation, okay? Something that we won't explore later. But another aspect which is also related to this one, but it's a different issue, is the critical dependency on initial conditions. So suppose that you have these three state equations, three state equations in x, y, and z. So the state variables are x, y, and z. And there is a parameter, let's select it to be 28. So this looks quite peaceful. It looks like quite peaceful. So we do a simulation in which all the state variables have the value of 5. So you have this simulation. This is just one of the state variables on the top. Now, you increase the initial condition of the first variable x of 0 by 0.1%. And you see what happens? You have this other simulation. So in the beginning, you are having a solution which is not so different. But after a while, after a lot of time actually, you start seeing that the behavior behaves completely different, okay? Now, this is typical of nonlinear systems and had a lot of implications. In particular, this is the situation that happens when you try to forecast the weather. So you can say, well, the weather is determined by the state of the atmosphere, and the state of the atmosphere is pressure, temperature, and water concentrations. So if I build a grid, I imagine a grid, the atmosphere built according to a grid, and at any point I know the temperature, I know the pressure, and I know the concentration of water. Then I write the equations that correspond to, on one side, conservation of mass, then conservation of energy, and then conservation of momentum, because you have wind, so you need to consider also the momentum. And you integrate these equations, and you can know what is the weather that is going to, whether there is going to be a sunshine in the day of your wedding, or whether it was raining 2 centuries ago or something like that. Actually not. And you can't do it because of this effect of the sensitivity with respect to initial conditions. So in nonlinear systems, you can have systems that by having tiny changes of the initial conditions, you have a wild change in the solutions. This was something that was discovered not so long ago, about 60 years ago, and caused a revolution also in the way we think about the world. If you go to the 19th century, the giants that developed the mechanics, mathematical mechanics, like Lagrange or Laplace, these people were convinced that if you are able to know all the particles in the universe, the position and velocities at one instant, and all the equations that could be derived from the forces that act on these particles, then you could know everything from minus infinity up to plus infinity. It was a kind of being God. So God was a big mathematician able to integrate a big set of differential equations, knowing all the details and knowing all the initial conditions. And complexity was a system with many parts. So you measure complexity by measuring the number of states. Now, after this phenomena that I just mentioned popped out of extreme sensitivity with respect to initial conditions, popped out in the 60s of the last century, of the 20th century, people started to realize that complexity may arise in systems with a very small number of states. Actually, you can find them in first order systems. And the only thing is that they are extremely sensitive. So you can have very complex phenomena of the state evolving in time, very complex functions of time being the solution of these systems due to their peculiar structure. And the number of states is very reduced. Okay, so this gave origin to a number of studies that the popular name is chaos. Okay? And it's not surprising that the guy who introduced this example was a materiologist. Actually, this equation started as a model for the atmosphere, a very simplified model for the atmosphere. But even in this very simple case, we have a tremendous complexity behavior. Okay, so this is something again that we are not going to study. Furthermore, we are assuming that our state models will be well behaved and do not present this type of phenomena, chaotic phenomena. Now, before we end this lecture, a few words about oscillations and limit cycles. So what is a limit cycle? It's a closed trajectory in state space. It corresponds to periodic solutions in time. Okay? A stable limit cycle is a limit cycle such that all the trajectories that start near approach it. If they do not approach it and they deviate from it, they are an unstable limit cycle. So stable limit cycles correspond to observable oscillations in terms of being physically possible to observe. Let me give you one example, one classical example, the van der Poel equation. So the van der Poel equation is this one. So y is our unknown and mu is a parameter. And if you define states to be x1 equal to y and x2 equal to the derivative of y, you get this state model, which is equivalent to the van der Poel equation. Now, let's see what happens. And what happens is something like this. So the variables in the axis here are x1 and x2. So this is the phase portrait. And if you start in this line, you will remain in this line, and you eventually return to it. Okay? So you have a periodic solution, and this is a limit cycle. Now, if you start a little bit away from the unit cycle, the limit cycle, so at position A, you spiral closer and closer approximating the unit cycle. And this is also what happens when you start inside the unit cycle. So you spiral closer and closer to the unit cycle. So this is a stable limit cycle. Actually, the van der Poel equation appears in many situations, models many oscillators of practical interest, in particular in electronics. And also the equilibrium point at the origin, it's unstable because if you deviate a little bit from it, you spiral away. Actually, we use this equation when we introduced the notion of stability, of the Apanov stability. If you look in time, these are the curves that you get. Okay, so this is the end of this lecture. What were the important points? The important points, I can summarize it in actually 2 points. First, how can we write the state equations for nonlinear systems? Well, x dot equal to a function that is in general nonlinear of the state and the input. And you also have an algebraic equation y equal to a function of the state, possibly also of the input. This is the first thing. The second thing is that we should be careful so that the state model is well behaved. It has sense, in particular with respect to existence of solutions and sensitivity with the initial conditions, chaotic phenomena, and so on. If this phenomena are present, then you should be quite careful. And these are the 2 points. Thank you for your attention.